Hello everyone, very good evening. Welcome to the most comprehensive preparation app for all exams, BYJU'S Exam Prep, and warm welcome to the series Mastering Concepts for GATE 2023. Join the session quickly and mark your presence, all dear friends. I am waiting for you all to join the session. So quickly join the session, guys. In today's session, we will be discussing another error control mechanism, that is Hamming code. Yesterday, in the last class, we have discussed one error detection code, that is CRC, cyclic redundancy check. Today, we will be discussing Hamming code. So, before I start, I invite everybody, whoever are preparing for GATE 2023, to join the session. Quickly join, guys. I am waiting for you all to join the session. And those who have joined, please do mark your presence. This is quick brief about me. You can find my details here. Guys, on 22nd May at 12:30 p.m. we are doing a workshop to give you tips and tricks for how to secure under AIR 100 in the upcoming GATE exam. So, if you are in third year or final year who is aspiring for GATE 2023, who is going to appear, definitely it would be very useful session for you. So without fail, join this session. Our experts will be giving you tips and tricks so that if you add your hard work to them, you will definitely be under 100 in GATE 2023. All right. So guys, I want everyone, whoever have joined, please confirm your presence, and also please do confirm, am I visible and audible to you? Those who have joined the session, please do like, share and subscribe. Try to invite all your friends through Telegram, WhatsApp, Instagram, Twitter, Facebook, so that they also know about this session happening and join. All right. Guys, we have understood that to handle errors, we have basically two types of techniques as discussed yesterday. One is error detection code, other is error detection and correction code. Means detection code will find only the presence, whereas detection and correction code will find both presence and position of error. We have four types of detection codes as VRC, LRC, CRC and checksum, and error correction code is Hamming code. So today's topic is Hamming code. So without any delay, we will start this Hamming code discussion. Before that, let me welcome Kiruti. Very good evening. Guys, we know Hamming code is a correction technique. Means what? It will find presence and also position of an error. So in the CRC technique, we have already seen how we are able to handle errors. To the data that we wanted to send, we will add some bits which are called redundant bits. After adding that that particular formed content we are sending to the receiver. So when we wanted to send the data, that data to be transmitted, we call as data word. Let it be D. But for controlling errors, redundant bits are appended to D. So when D and R are together, then what will be formed? A code word C will be formed. That is what transmitted. That is what transmitted. Hi Sarvesh Kumar Pal, good evening. So what gets transmitted, guys? A code word gets transmitted. And in this code words, we will have valid code words, invalid code words. So we say XOR of any two valid code words is also a valid code word. How you say which is valid or invalid? We know redundant bits for the D are added. Let's say this is all D. To this, redundant bits are added. These redundant bits keep changing when we are transmitting over a network with many intermediate stations, because at every data link layer this redundant code may be freshly calculated. But what about this D? This D will not change. So let's say we are having some 7 bits of data word, 3 bits of redundant word, then totally we are getting a 2 power 10 bit code word. So we can say there are 2 power 10 code words are possible. 2 power 10 code words are actually possible, but among them valid code words means only the combinations of this R we can say valid, rest all we say invalid. Got it? That is how we say which is valid, which is invalid. So if we get any two valid code words, if you apply XOR to them, the result is also considered to be a valid code word. Okay? Now, how this hamming method is applied? Firstly, let us see how you get this hamming code procedure over textbooks or over web source. This is how you will find. The hamming method use extra parity bits to allow identification of single bit error. So how do you find? First, write positions starting from 1, not from 0, starting from 1. Then mark all these bit positions which are powers of 2 as parity bits. So where you append parity bits? In the position of 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4, etc. All other bit positions are for the data word. Means whatever are remained like 3, 5, 6, 7, 9, 10, 11, 12, 13, 14, 15, etc. Now we have to find what should be that parity bit in 2 power 0, 2 power 1, 2 square, 2 cube and so on. So each parity bit calculates the parity for some of the bits in the code word. Means we will pick some of the bits in the data and we will do XOR operation and we will find the parity bit. For every parity bit, what bits we pick from the data keep changing. that position of the parity determines sequence of bits that alternately checks and skips. Now, for position 1, what we check? Check one bit, then skip one bit, check one bit, and then skip one bit, and so on. Means check bit 1, 3, 5, like skip one bit means second bit is skipped. Pick 3, 4 is skipped. Pick 5, 6 is skipped. Pick 7. Like that you have to do. And how do you check position 2? Check 2 bits, skip 2 bits. Similarly for position 4, check 4 bits, skip 4 bits. Position 8, check 8 bits, skip 8 bit. So like this, if you see, it may be little confusing, right? So what it is saying, we will directly understand with an example. Suppose we wanted to transmit this. So this is what the data word. Now you have to arrange this data word along with redundant bits. Okay. So I am taking positions. We start positions from 1, not from 0. So first position is 2 power in 2 power ith position, we will place redundant bits. So let's say the first redundant bit is R1. We know I starts from 0. So 2 power 0 means first position, that is R1, and 2 power 1, that is second position. So R2 will be in the second position. And is position 3 is 2 power is the power of 2? No. So here we place the first data bit 1. 4, which is 2 square. So it is a powers of 2. So fourth position is redundant bit position. So R3. Fifth position is not redundant bit position. So place next bit 1. Sixth position is not redundant bit position. So place next bit 0. Seventh 1. So I am placing these data bits as it is. Eighth position is again redundant bit position. So I will place R4. Now ninth bit is not redundant bit position. So I will place 0. 10, 1. 11. So 0 is placed, 1 is placed. 11 is 0. 12, 1. 13, 1. So with this, actually our data is completed. So if we have more data, if that data expands to 16th position also, then we would have added another redundant bit position, but our data length is requiring or demanding only 4 redundant bits. So total positions, how many we have? 13. Now what it says, those positions you write in the binary form. In the binary form, write these positions. So 1 means 0, 0, 0, 1. 2, 0, 0, 1, 0. 3, 0, 0, 1, 1. 4, 0, 1, 0, 0. 5, 0, 1, 0, 1. 6, 0, 1, 1, 0. 7, 0, 1, 1, 1. 8, 1, 0, 0. 9, 10001, 1010, 1011, 1100 and 1101. This is how we got. Right? So this is 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Now what the algorithm is telling, for finding the parity bit values, you have to pick. So if you want to find redundant bit 1, you have to pick the positions where you have ones in the units place. So that is how it is said, pick one, skip one, pick one, skip one. So alternative. In that, first position we have is R1. We are finding that, so sender will skip it, receiver will include it. Okay, sender skips it, receiver includes it. So now skipping this by the sender, other positions are 3rd position, 5th position, 7th, 9th, 11th, 13th. What you have to do? You have to do XOR operation between all those bit values. So 3rd position we have 1, 3rd position we have 1, 5th position we have 1, 7th 1, 9th 0, 11th 0, 13th 1. Now count number of ones, 1, 2, 3, 4, even number of ones. When even number of ones are there, what XOR says? The output should be 0. Right? So R1 is 0. Now R2, how do you check R2? Find where you have ones in the tens place. That is what? Pick 2, skip 2. Yes, Sarvesh. So second position is for R2. We are finding it. So sender skip it, sender exclude it, receiver include it. So excluding that, what positions we have? 3rd position we have, right? 6th position we have, 7th position we have, 10th position we have, and 11th position we have. Now 3rd position is having 1, 6th position is having 0, where you have to check here. 7th position is having 1, 10th position is having 1, 11th position is having 0. Now count number of ones. 1, 2, 3. 3 ones are there, which is odd number. 3 means odd number. So for odd number of ones, XOR gives what output? 1. So R2 will be 1. Kiruti, that is what? These two we are taking, skip 4, 5. Then take 6, 7, skip 8, 9. Take 10, 11, skip 12, 13. Our data suffice 13 only. So like this we are taking 2, 3, 6, 7, 10, 11. But why I have not included 2 here? Because sender exclude it, because you wanted to find R2 in such a way, like if you want to include that final value, you should get 0. So by adding what, you will get 0. In that way you can understand. Okay, that means like this. So R1 XOR, first position is R1's position, here second position is R2's position. So by adding what, you will get 0. By adding 0 for R1, by adding 1 for R2, you will get. So R1 is 0, R2 is 1. Now R3. How do you check R3? Find where you have ones in the hundreds place, means in the from LSB in the third place. So these are the bits we have ones in the tens place, this is hundreds place. So this is what easy to understand. Now 4 is what R3's position. So by adding this, you should get the result 0. So R3 XOR fifth position is 1. So I am directly writing. Sixth position is 0. Seventh position is 1. Then 12th position bit is 1. 13th position bit is 1. Here count number of ones, 1, 2, 3, 4. Already there are even number of ones. So what should be R3? 0. So R3 should be 0. Now for R4, where R4 is at 8th position. For 8th position, where you have 1 in the MSB, right? So find out where you have ones in the MSB. For 8, 9, 10, 11, 12, 13. So include them. 8 is already included. Now 9th position we have 0. 10th position we have 1. 11th we have 0. 12th we have 1. 13th we have 1. So 1, 1, 1. 3 ones. So by making R4 as 1, the final number of ones becomes 0. So by R4 will be 1. So what is the code word to be transmitted when this is the data word? So code word comma C is equal to 1101 01 10 10 110. Here in this, redundant bits are scattered over the data word. Now this is sent to the receiver. Receiver follow the same procedure. He should get what? All R1s. He should get all R1s zeros, isn't it? He should get all redundant bits zeros. If he don't get redundant bits zeros, then what is the case? Always the error is set to be at R1, R2, R3, R4 like this at this position for the receiver. So if all redundant bits are zeros, it says error at 0th position. However, there is no 0th position. That's why we are starting from 1. So if any redundant bit is 1 or multiple redundant bits are 1s, that will give you the position of error. So Hamming code is finding the position also. Once you find the position, it is easy to correct, because 1 is error means correction means what? Make it to 0. 0 is error means correct it, make it to 1. So correction is simple. Finding the position is what difficult, right? So here, as we have just 9 data bits, by arranging like this, we could be able to find that there are the requirement of redundant bits is 4. But what if there is a big message, big data? How I can find how many redundant bits are required? Are you getting? So for that we will just give me a moment. Just give me a minute, guys. Yeah. Sarvesh, in the binary form of those positions, in the third positions, these I am calculating. See, from LSB, in the third positions where I have ones, 4 I have taken, fourth position I have what? R3. Fifth position 1, sixth position 1, sorry 0, seventh position 1, and then okay, 12th position 1, 13th position 1. So R3 1 0 1 1 1. Here I have number of ones even. So to keep it still even, R3 value should be 0. Means we can say we are following even parity. Okay. Now guys, as I was telling, we have just 9 data bits. So by arranging this in this form, we could be able to find that 4 redundant bits are required. So what if we have many data bits? So let number of data bits in data word D, let it be small d. Okay. Then how you calculate number of redundant bits required? So let number of redundant bits be R. So how we calculate? There is a formula. If 2 raised to R greater than or equal to D plus R plus 1, or somewhere you may find 2 power R minus 1 greater than or equal to D plus R, because both are same. So let I am having the data bits, let us suppose I am having 500 bits. So minimum number of redundant bits required. So what is R? We will calculate. 2 raised to R should be greater than or equal to 500 plus R plus 1. That means 2 raised to R should be greater than or equal to 501 plus R. So here if I keep R value as 1, 2, 3, like that, if I try, suppose if R value is 7, 128 greater than or equal to 501 plus 7, false. So take R value 8, 256 greater than or equal to 501 plus 8, false. So take R value 9, 512 greater than or equal to 501 plus 9, 512 greater than or equal to 510, true. So for what R this satisfied? For what minimum R value? 9. Hence we require minimum 9 bits if we have 500 data bits. right? So this is what the formula you can use for finding minimum number of redundant bits. And we have two more formulae kind. We can say the number of bit differences between code words, what we say that as Hamming distance. For example, let the code word C1 is equal to 110101. Code word C2 is equal to 10011110. Now, what is a Hamming distance? How do you get? Manually, you can actually verify by how many bits they are different. But in computer programming, how you can do that? Do XOR between them. So when you do XOR, we will get, if same number of bits we get 0, different bits we get 1, no? So we get 0, 1, 0, 0, 1, 1. Now calculate number of ones in the result. Number of ones is Hamming distance. So how many ones we have in this result, XOR result? 3. That means the number of bit differences, by how many bits any two code words differ, that is what you say Hamming distance. Let's say it as D. So to detect up to D errors, the Hamming distance need to be D plus 1, and to correct up to D errors, that Hamming distance need to be 2D plus 1. These two are another important formulae kind which will be useful for us in the GATE for solving questions. Now, this is what a 2004 GATE question. Go through the question once. Consider a parity check code with 3 data bits and 4 parity bits. 3 data bits, 4 parity bits. 3 of the code words are given. Which of the following are also code words? So we are given with 3 code words, C1, C2, C3. From these we have to find out what are the other code words valid. I said, if you remember, XOR of any 2 valid code words is also valid. Do you remember? XOR of any 2 valid code words is also valid. Right. So how do you find which are valid code words here? We will take the given code words and we will apply XOR among them. Okay? All right. Let us do. Let the given code words be these. So let these are C1, C2, C3. So apply XOR among them. C1 0 1 0 1 0 1 1. C2 1 0 0 1 1 0 1. So do XOR. You will get 1 1 0 0 1 1 0. Do you have that here? Let it be C4. It is also a valid code word. Okay. Now apply XOR between C1 and C3. 0 1 0 1 0 1 1 triple 1 triple 0 1. So it is 1 0 1 1 0 1 0. Do we have this? Yes. So let it be C5. Let us do XOR between C2 and C3. 1 0 0 1 1 0 1 triple 1 triple 0 1. Do XOR 0 1 1 1 1 0 0. Do we have this? 0 4 1s 0 0? No. Okay, no problem. C6. So we have got three new valid code words. Now let us do XOR between C4 and C3. C4 we got is 1 1 0 0 1 1 0. C3 is triple 1 triple 0 1. So when you do XOR, it would be 0 0 1 0 1 1 1. Do you find this? Yep. So it is also a valid code word. Now do XOR between C5 and C2, because C5 is XOR of C1 and C3. So the remaining you do C5 and C2. C5 is 1 0 1 1 0 1 0. C2 is 1 0 0 1 1 0 1. It is 0 0 1 0 1 1 1. Do you have this? 0 0 1 0? No. Right? Okay. Now let it be some C7. Now apply XOR between C5 and C6. So here I got C5, C6, and now let me apply XOR between C5 and C6. So C5 is 1 0 1 1 0 1 0. So it will give you 1 1 0 0 1 1 0. Do we have this? Okay, no. One is valid, 3 is valid. Yes, definitely yes. Now let us do XOR between. Okay, we don't find this there. Okay, now let us do, let us take it as C8. When we are getting new code word, you mark it as a new with a new identification. Now let us take C7 and C8. C7 is 0 0 1 0 triple 1. C8 is 1 1 0 0 1 1 0. So it will give 1 1 1 0 0 0 1, which is again C3. This is again C3. Like this, when you keep doing all the combinations, you will find which is valid. So what are valid code words? Only 1 and 3. Yeah, 1 and 3. Yeah, among the given options we don't have this. Okay, 0 0 1 0 triple 1 we have. Okay. Yeah. Yes, we have it. Okay. Now another question, that is a 2007 gate question. An error correcting code has following code words. You can see 1, 2, 3, 4, 5 code words are given. What is the maximum number of bit errors that can be corrected? We just discussed, if we have Hamming distance d, to correct up to d errors, correction demands 2d plus 1 Hamming distance, right? Minimum Hamming distance. Kiruti, if you just do 2 more, they just keep repeating. Okay. Now guys, these are the code words we have. Let me mark them as C1, C2, C3, C4, C5. Okay. Now what we have to do? Find the minimum Hamming distance. So what is the Hamming distance between C1 and C2? Between C1 and C2, find the Hamming distance. C1 is all zeros, C2 is 4 zeros, 4 ones, so it is 4. Between C1 and C3, C1 is all 8 zeros, C3 is alternated zeros and ones, so it is also 4. C1 with C4, C1 with C5. The other possibilities, C2 with C3, C2 0, 1, 0, 1, 0, 1, 0, 1, so 4. C2 with C4, it is also again same, 1, 0, 1, 0, 1, 0, 1, 0. C2 with C5, here you see it is exactly complement of the C2, C5 is, so we have all 8 bits difference. Then C3 with C4, what is the Hamming distance between C3 and C4? 8, because that is again complement. C3 and C5, 4. And finally C4 with C5, 4. So what is the minimum Hamming distance among 4 and 8? That is 4. So 2d plus 1 is 4, 2d is 3, so what should be d? 3 by 2, that means 1. Don't say 1.5, 1. So how many errors can be corrected? 1 error, because we will take minimum Hamming distance. Got it? Right. So guys, this is how we will solve Hamming code related questions. I hope it is clear for you. You feel little more confident now after this class with Hamming code technique. So yesterday we have discussed CRC, error detection code. Today we have discussed Hamming code, which is error detection and correction code. So these two are what frequently asked topics of error control from data link layer in computer networks. That's why in this series I have took this. I hope it is very clear for you. If so, please do like the session and share it with your friends, and do subscribe to our BYJU'S Exam Prep channel. And this is our Telegram group link. Please do join this Telegram group for any guidance, any suggestions related to your career or GATE preparation, and for PDFs and doubts clearance, and also for the schedule of my classes, when what classes keep happening. Okay, and also please share this Telegram group with your friends, guys, as much as possible. So because it's a student community, all students who are preparing for the GATE exam are there in that group, so you can just exchange your thoughts. It's a kind of peer group learning, so it would be very useful for you. All right, I hope you liked the session. See you in the next session. Till then, have a great time. Before you sign off, don't forget to like, share and subscribe. See you in the next session. Till then, have a great time. Take care. Good night, everybody. Bye bye. Thank you.